Picture the moment. It is before dawn. The Florida coast is still dark, the Atlantic a flat black mirror stretching toward a horizon you cannot see. And then, slowly, impossibly, a column of white fire tears open the night sky. The ground shakes. Not just the ground, your chest, the air itself. Windows rattle in motels 11 kilometers away. Birds scatter from the tree line. People standing on causeways and bridge rails and the hoods of parked cars throw their hands over their ears and stare upward with their mouths open. And riding that fire, on top of the most powerful rocket ever successfully launched in human history, are 4 human beings. 4 people who volunteered to go somewhere no human has gone in over half a century. They are heading to the moon. But not just the moon. Because what the Artemis program was always really about, what every press conference, every congressional briefing, every NASA administrator has repeated like a mantra for the better part of a decade, was never just the moon. The moon was practice. The moon was the dress rehearsal. The moon was us checking whether the machine works before we point it at something 200 times farther away and say, Mars. And for a while, that story held together beautifully. The timelines, the mission concept renderings, the astronaut portraits released with carefully composed smiles, the speeches about humanity standing on the edge of becoming a multi-planetary species. The whole thing had the feel of destiny made visible, of history that knew where it was going. But destiny, it turns out, has a way of pushing back. Because what Artemis 2 revealed, what it found beyond the protection of Earth's magnetic field, in the cold silence between worlds, was not confirmation that we are ready for deep space. It was something much harder to hear. It was a list of problems we did not fully solve, dangers we did not fully understand, failures we did not see coming, and warning, signs written in data, in material science, in human biology, in engineering anomalies and medical readings and mission logs. Warning signs that, if we are being honest with ourselves, we should have been more worried about before we ever lit that rocket. This is not a story about a mission that failed. Artemis 2 did not fail. The crew came home. The spacecraft came home. By every official metric, the mission was a success. But success, sometimes, is just the story you tell on the press conference podium. The other story, the one told in technical debrief rooms, in NASA safety board documents, in the quiet conversations between engineers who have spent their careers studying what space does to machines and to people, that story is more complicated and a lot more unsettling. So let us tell that one. Chapter 1: The Weight of a Promise. To understand what Artemis 2 revealed, you have to understand what Artemis was supposed to prove. And I mean that in the deepest sense. Not just what it was supposed to accomplish technically, operationally, on a checklist, but what it was supposed to mean. Because NASA did not design the Artemis program in a vacuum. It designed it in the shadow of 5 decades of stagnation. 5 decades since Apollo 17 lifted off from the lunar surface in December 1972, since the last human being climbed the last ladder of the last lunar module and left the moon forever. And in that time, human spaceflight had not exactly been standing still, but it had not been going anywhere either. We built a space station. We flew the shuttle 135 times. We conducted extraordinary science in low Earth orbit, but we had not left. Not really. not beyond the safety net. Low Earth orbit sits, at most, about 400 kilometers above the Earth's surface. That sounds impressive, until you consider that the Moon is roughly 384,000 kilometers away. It is not even the same order of magnitude. It is a different category of ambition entirely. And for 50 years, we had stayed in the backyard. Artemis was the moment we were supposed to step outside the gate again. The program's stated goals were clear: return humans to the Moon by the mid-2020s. Establish a sustained lunar presence, meaning not just visit, but actually stay, cycle crews in and out, build the infrastructure for a permanent outpost. And then, using everything learned from doing that, use the Moon as a metaphorical and eventually literal launchpad for crewed missions to Mars. The name itself was chosen carefully. Artemis is the twin sister of Apollo in Greek mythology. The message was deliberate. This is the continuation of something that was interrupted. We are picking up the thread. We are doing what we should have kept doing all along. And the centerpiece of this new era was a spacecraft unlike anything that had flown before. The Orion Multi-Purpose Crew Vehicle, the Space Launch System, the SLS, which, when fully stacked, stands 98 meters tall and generates more thrust at liftoff than any rocket since the Saturn V. Engineers at NASA and their contractors had spent the better part of 2 decades, and depending on how you count the development costs across program iterations, somewhere between $23 and $40 billion building these systems. The numbers stagger the imagination, but the ambition behind them staggers it more. It is also worth pausing here because it is important context for everything that follows. To acknowledge what that development history actually looked like from the inside. The SLS rocket did not arrive polished and purposeful from a clean design lineage. It arrived carrying the accumulated fingerprints of at least 4 previous programs that were canceled, restructured, or absorbed into it along the way. The Constellation program, the Ares rockets, the Orion capsule went through design iterations so numerous that engineers from the early development days would barely recognize the final vehicle in its external configuration. Every new presidential administration brought a new vision. Every new vision brought a new set of priorities, a new schedule, a new set of congressional negotiations over which contractors in which states would receive which portions of the work. The result was a system that was, by the time it launched, genuinely impressive in many ways and genuinely compromised in others. A product not just of engineering decisions, but of political ones. Not just of what the best technical solution would be, but of what the political environment of 2 decades of appropriations cycles would allow. This is not a criticism unique to NASA. It is simply the reality of how large government-funded scientific programs are built in democracies. But it is essential context, because some of the anomalies and surprises that Artemis II encountered, the heat shield behavior, the software edge cases, the system integration issues that showed up in the mission timeline, have roots that trace back not to individual engineering mistakes, but to the structural conditions under which the program was built. Systems that carry 20 years of design decisions across multiple administration changes carry an enormous amount of what engineers call technical debt. Compromises and workarounds, and legacy architecture choices that made sense at one moment in the program's history and created unanticipated complications at a later one. The numbers stagger the imagination, but what the numbers bought is complicated. Because the people driving this program were not just thinking about the moon. They were thinking about what the moon represents in the larger narrative of human survival. They were thinking about what it means to be a species permanently confined to one planet. One fragile, finite, accident-prone rock orbiting one star in the outer arm of one unremarkable galaxy among 2 trillion others. They were thinking about extinction risk, about the long-term survival of human civilization, about the argument, made compellingly by Carl Sagan decades ago and echoed more recently by scientists and entrepreneurs across the spectrum, that being a single-planet species is not a stable, long-term condition. One large asteroid impact, one cascading climate failure, one pandemic with a higher kill rate, one unchecked geopolitical catastrophe, and the story of human consciousness ends permanently. The counter-argument to that fragility is not political or even primarily technological. It is existential. It is biological. It is territorial in the most cosmic sense of the word. It is simply, we need to go. And Artemis was supposed to be the beginning of the going. Artemis 1, launched in November 2022, was the uncrewed proof of concept. It sent the Orion capsule on a 25-day loop around the moon, a free return trajectory that brought it closer to the lunar surface than any crewed or uncrewed vehicle had traveled in that direction since Apollo, and it came home. It splashed down in the Pacific. It was, by most accounts, a triumph. The rocket worked. The capsule worked. The ground systems worked. Everyone breathed. But even in that triumph, something happened. Something that engineers stared at for months afterward, that led to design reviews and testing programs and quiet, serious conversations about whether the next mission, the one with actual human beings inside, should be modified before it flew. We will get to that. Trust me, we will get there. Because when Artemis 2 finally launched, it was carrying not just 4 astronauts. It was carrying the weight of that promise. The weight of 2 decades of development and political compromise and budget battles and schedule slippages. The weight of the argument that we are ready, that the technology is mature enough, the knowledge deep enough, the systems robust enough to begin the real push into deep space. And what the mission found in the data and in the spacecraft and in the bodies of the crew was that the weight of that promise is heavier than any rocket can lift. Some of it, in ways we did not see coming, may be too heavy to lift at all. Chapter 2, The Edge of the Invisible Fortress. Here is something most people never think about. Right now, as you watch this, you're inside a fortress, an invisible one. A fortress with no walls, no gates, no obvious boundaries, but one that is quite literally keeping you alive. It is called the magnetosphere, and it is Earth's magnetic field, generated by the churning convection of molten iron and nickel in our planet's outer core, spiraling outward into space in a shape that looks roughly like a teardrop. Blunt on the side facing the sun, stretched and elongated like a vast comet tail on the side facing away. It extends at its widest, roughly 65,000 kilometers toward the sun and millions of kilometers in the opposite direction. A vast invisible shield enveloping the entire planet in a cocoon of deflected particles and redirected energy. And its purpose, its ancient, accidental, irreplaceable purpose, is to protect everything on this surface from one of the most lethal things in the universe. Radiation. Not the kind of radiation you instinctively picture when someone says the word. Not X-rays from a medical scanner or gamma rays from a nuclear weapon, though those are members of the same family. I am talking about cosmic radiation, the stuff that fills interstellar space the way air fills a room, everywhere, invisible, and in the right dose, lethal. High-energy particles, protons, alpha particles, heavy atomic nuclei stripped of their electrons and accelerated to tremendous velocities, traveling at significant fractions of the speed of light, carrying energies millions of times higher than anything a particle accelerator on Earth can produce. They come from two main sources. The first is our own sun, solar energetic particles accelerated during solar flares, and coronal mass ejections, events that can blast enormous waves of charged particles across the solar system in a matter of hours. The second source is far more exotic and far harder to stop. Galactic cosmic rays, originating from supernovae and neutron star collisions, and other catastrophic events scattered across the Milky Way and beyond, carrying energies so extreme that they are essentially impossible to fully shield against with any material currently known to science. On Earth's surface, we are protected from essentially all of this. The magnetosphere deflects the charged solar particles, bending their paths away from the planet like a stone, deflecting a stream of water. What gets through is largely caught by the atmosphere. 10,000 kilograms of air above every square meter of your body, which absorbs and scatters the rest. Your annual radiation dose on Earth's surface is roughly 2 to 3 millisieverts. That is the standard medical benchmark. That is safe. That is where we evolved to live. Step outside the magnetosphere, and the mathematics change completely. In deep space, in the region between the Earth and the Moon, and beyond, there is no magnetosphere. There is no atmosphere. There is nothing between you and the full, unfiltered power of everything the universe is radiating across the void. Your radiation exposure in deep space, depending on solar activity and the phase of the 11-year solar cycle, can run between 0.5 millisievert and 1 millisievert per day. Every day, continuously, which translates to between 180 and 365 millisieverts per year from background cosmic radiation alone, potentially 100 times your annual dose on Earth's surface. And during a major solar particle event, a large flare or a coronal mass ejection aimed directly at your position in space, the dose rate inside an inadequately shielded vehicle could spike to lethal levels within hours. Not days, not weeks, hours. Let that settle for a moment. This is not a theoretical concern buried in a risk assessment footnote. This is a known, documented, categorically verified physical reality of deep space that has been understood since the Apollo era. Apollo astronauts reported seeing flashes of light with their eyes closed in the darkness of the lunar module, cosmic ray particles passing directly through their skulls and striking their retinas. Gene Cernan reported them. Neil Armstrong reported them. Buzz Aldrin reported them. Virtually every Apollo astronaut who went beyond low Earth orbit saw the flashes. Physics interacting directly with human biology in the dark between worlds. But in the Apollo era, mission durations were short. The total mission time for the longest Apollo flight was just over 12 days, short enough that the radiation exposure, while measurable and higher than Earth's surface baseline, was considered acceptable within the risk framework of those missions. The Artemis program is not designing for 12-day missions. It is designing for missions of 30, 60, 90 days and beyond. It is designing for lunar orbit stays aboard the Gateway space station. It is designing, eventually, for a Mars transit, a journey that would take 6 to 9 months each way, followed by a surface stay of potentially 18 months before the orbital geometry allows a return. Total mission duration, potentially 3 years in the deep space radiation environment. And here is where the numbers begin to do things that make aerospace engineers go very quiet at conferences. NASA's current career radiation limit for astronauts, the limit designed to keep lifetime excess cancer risk below 3%, sits at approximately 600 millisieverts over a lifetime for a 35-year-old woman and somewhat higher for men, due to differences in cancer risk profiles by tissue type. After a Mars mission using current shielding technology, an astronaut could accumulate between 600 and 1200 millisieverts in a single mission, meaning that for many crew members, a Mars mission under current conditions would either meet or exceed their entire career radiation limit. A one-way ticket in terms of future spaceflight eligibility. Possibly a one-way ticket in terms of long-term health outcomes. And that is the calculation without a major solar particle event along the way. Now, Artemis 2 was not a Mars mission. The 10-day lunar trajectory meant the crew spent only a fraction of that time in the full deep space radiation environment, far too short for acute radiation effects to threaten the mission. But here is why this matters specifically for Artemis 2. The mission's purpose was, in part, to validate the systems and the data models in preparation for longer missions. The radiation, monitoring hardware aboard Orion, sensors embedded in the spacecraft structure, personal dosimeters worn by each crew member, real-time particle detection instruments feeding data to mission control, was designed to characterize the deep space radiation environment as the vehicle moved through it. Not to measure it in the abstract, but to measure it in this vehicle, with these shielding materials, on this trajectory, with these human bodies inside. And what those measurements confirmed was both less and more reassuring than the public briefings suggested. Less reassuring in one specific and important way. The galactic cosmic ray flux encountered during the mission period was fully consistent with what the predictive models had projected, which is not good news because the models were already concerning. The data did not reveal a catastrophic surprise. It confirmed a difficult reality. Deep space radiation over longer missions remains one of the most serious unsolved problems in human spaceflight. Not unsolved in the sense that nobody is working on it. Unsolved in the sense that nobody has an answer, yet that works inside a spacecraft with a feasible mass budget. There are proposals. There are research programs studying pharmaceutical countermeasures, drugs that might enhance the DNA repair mechanisms of human cells, making them more resilient to radiation damage. There are engineering proposals for water walls aboard spacecraft, using the hydrogen density of the ship's own water supply as a cosmic ray scattering layer. There are conceptual proposals for superconducting magnetic shielding that would generate a miniature artificial magnetosphere around the spacecraft itself. Every one of these proposals is real. Everyone carries serious engineering or physiological challenges. Not a single one is ready for operational use on a deep space mission today. And Artemis 2, in its quiet, data-driven way, reminded us of all of that with fresh precision. The specific radiation measurements recorded during Artemis 2's transit were subsequently published in technical briefings and represent some of the most detailed, real-time deep space dosimetry data collected from a human-rated vehicle since the Apollo missions. The instruments aboard Orion measured not just total dose, but dose rate variation, allowing researchers to observe in real time how the particle environment changed as the vehicle crossed from inside the magnetosphere outward into free, deep space. The transition was not a clean step change, but a gradient, a region where the magnetospheric protection diminishes over tens of thousands of kilometers, and the measured particle flux climbs in ways that track well with the theoretical models for total dose, but show event-by-event variability that no model completely captures. Small solar particle events, not large enough to trigger a radiation shelter alert, registered as detectable spikes in the dosimetry record. Brief, modest, medically inconsequential for the short mission duration. But for a crew spending 6 months in that environment on a Mars transit, every one of those spikes would be a running total, accumulating against a lifetime career limit. The radiation picture from Artemis 2 was, in the language of risk assessment, a better characterized risk. More data, more precision, more confidence in the models. Not a solved risk, not a mitigated risk. A risk whose dimensions are now somewhat more sharply drawn. But a radiation, as serious as it is, as unresolved as it remains, was not the most dramatic finding of the mission. For that, you need to look at what happened to the spacecraft itself. Chapter 3: The shield that wasn't supposed to do that. In October 2022, about a month before Artemis 1 launched, NASA made a decision that did not get nearly the public attention it deserved. They changed their re-entry plan. The original trajectory for Orion's return from lunar distance called for a relatively direct ballistic re-entry, the capsule arsing down through the upper atmosphere, decelerating via aerodynamic drag, protected from the temperatures of re-entry by its heat shield. Physically identical in principle to the re-entries of Apollo capsules and every other crewed vehicle that has come home from deep space. But in October 2022, NASA switched to a technique called a skip entry. Instead of plunging directly into the atmosphere, Orion would enter the upper atmosphere, slow down partially, skip back out into space briefly, like a flat stone bouncing off the surface of a pond, and then re-enter for the final descent and splashdown. This technique reduces the peak deceleration experienced inside the capsule from around 10 Gs to around 4 Gs, which is far more survivable and comfortable for a crew. More importantly, for mission planning, it allows Orion to land in a much smaller target zone in the Pacific, close to the recovery fleet, rather than potentially touching down hundreds of kilometers off target in the open ocean. It is a clever, elegant piece of atmospheric physics, theoretically understood for decades, used by robotic sample return capsules, but never tested with the Orion capsule under real re-entry conditions from lunar distance and at lunar return velocity. Artemis 1 was that first test. And when the capsule was recovered from the Pacific and brought back for examination, when NASA engineers got their first close, detailed look at the heat shield that had just survived re-entry at approximately 40,000 kilometers per hour, the fastest re-entry of any crew-capable spacecraft since the Apollo era, they found something they were not expecting. The heat shield had lost material, not in the way it was supposed to. This is important to understand clearly. Heat shields are designed to lose material. They are built on the principle of controlled ablation. The shield material gradually burns away during re-entry, and in burning away, it carries the thermal energy of re-entry away from the capsule. The heat does not penetrate inward to the crew compartment because it is being constantly consumed by the sacrificial ablative layer on the outer surface. That is the entire mechanism. That is why the Apollo capsules survived. That is why Orion was built with a modernized formulation of the same material, a synthetic foam-like compound called AV coat, covering its blunt bottom face. The unexpected part was not that the AV coat ablated. The unexpected part was the pattern. Engineers had expected relatively uniform, smooth ablation across the heat shield face, material eroding at a predictable rate, matching the thermal models built over decades of aerothermodynamic testing and computational fluid dynamics work. What they found instead was dramatically non-uniform ablation. Chunks of the AV coat material, not surface erosion, not thin layers, but actual chunks, pieces with measurable depth and area, had detached from the heat shield and burned away during the skip entry maneuver in regions and in patterns that the pre-flight models had not predicted. For Artemis 1, unmanned, this was a serious and demanding data point, concerning, requiring urgent investigation, but not in itself a catastrophe. The spacecraft came home. Nothing was lost but the material itself and the confidence of the engineers who had signed off on the models. For Artemis 2, with 4 human beings inside, the stakes of that same anomaly were categorically different. The Artemis 2 crew would execute the identical skip entry maneuver. The same generation of heat shield would protect them. The same AV coat material that had shed unexpected chunks into the plasma of Earth's upper atmosphere would stand between the crew and temperatures exceeding 2,700 degrees Celsius during the skip entry, hot enough to melt steel in seconds, hot enough to vaporize titanium alloys, roughly half the surface temperature of the sun itself. There is very little engineering margin in that environment. The difference between a heat shield that works and a heat shield that does not is measured in fractions of a centimeter of remaining material and fractions of a second of peak heating exposure. To their credit, NASA treated the heat shield anomaly with extraordinary seriousness and thoroughness. They conducted an intensive multi-year investigation. They performed extensive ground testing of AV coat samples under simulated re-entry conditions in arc jet facilities, exposing coupons of the material to the thermal environments predicted for the skip entry phases. They constructed high-fidelity updated computational models of what the skip entry maneuver does to the thermal and mechanical stresses on the heat shield. How the 2 distinct periods of atmospheric heating, separated by the brief excursion back into near vacuum, create a thermal cycling environment with a different stress signature than a single direct re-entry. What the investigation concluded was that the non-uniform ablation was caused by several interacting factors. The unique aerothermodynamic signature of the skip entry trajectory created a boundary layer transition on the heat shield surface during the initial atmospheric pass. A change in the character of the supersonic gas flow across the material from laminar to turbulent, occurring in a spatial pattern that the pre-flight models had not accurately captured. In the transition regions, local heating rates and surface pressure loads were higher than predicted. The AV coat material in those regions was simultaneously exposed to higher temperature and higher mechanical shear stress than its bonding to the substrate had been designed to withstand. It responded by failing in shear and shedding. The engineering response involved modifications to the AV coat manufacturing process to improve material density uniformity and substrate bond strength, refinements to the computational aerothermodynamic models, and adjusted skip entry trajectory parameters to reduce the peak differential heating between the two atmospheric passes. And the Artemis II re-entry performed within acceptable parameters. The crew came home safely. By the official certification criteria, the heat shield passed. But here is the part that keeps serious aerospace engineers unsettled long after the recovery ships have docked. The models that were wrong before Artemis I were the same category of models used to certify the heat shield for Artemis II. Updated models, refined models, models with more physics, more fidelity, more data points baked in, but still models, still representations of reality rather than reality itself. And models, as Artemis I demonstrated without ambiguity, can be wrong in ways that do not become visible until the actual flight. There is a concept in systems safety engineering called the unknown unknown, the category of failure mode that is not in your risk register because you do not know it exists. You cannot plan for what you have not imagined. The AV coat boundary layer transition failure was, in the most important sense, an unknown unknown before Artemis I. Artemis I made it a known known, which is genuinely valuable, which is exactly what uncrewed test flights are supposed to do. But the question Artemis II forced engineers to sit with is this: how many unknown unknowns remain in the heat shield's behavior for future trajectories, future skip entry parameters, future conditions? For a crewed vehicle returning from lunar orbit at different velocities than the Artemis II trajectory, the aerothermodynamic environment is different again. The boundary layer transition will occur at different locations on the shield face. The peak heating rates will have a different temporal profile. The thermal cycling signature of the skip will be different. Those conditions have not been tested at full scale. They will be trusted to models that have already been wrong once in ways that mattered. The heat shield situation is a precise, technically specific window into a broader truth that Artemis II kept surfacing in dataset after dataset across the mission. The gap between our computational models of deep space operations and the physical reality of what actually happens when hardware and human bodies go out there is larger than the program's public narrative acknowledges. And for systems where the margin between a nominal outcome and a catastrophic one is as thin as the ablative layer between a crew capsule and a plasma environment at half the temperature of the sun, the size of that gap is not an abstraction. It matters. And we have not yet talked about what deep space does to the people inside that capsule. Chapter 4: What happens to a human body? When the Earth disappears, there is a threshold in space that most people have never heard of. It does not have a dramatic name. There's no ceremony when you cross it. The spacecraft does not shake. No alarm sounds. From inside the capsule, you would probably notice nothing different at all. You would be watching the instruments, running the checklists, eating from a foil pouch, doing exactly what you trained for years to do in exactly this moment. But outside, something fundamental has changed. You have crossed the outer edge of Earth's Van Allen radiation belts, the zone where Earth's magnetic field traps energetic particles in two great concentric rings around the planet, extending from about 1,000 kilometers above the surface out to roughly 60,000 kilometers. The inner belt is densely packed with high-energy protons. The outer belt is populated with electrons accelerated to relativistic velocities. Passing through them quickly, as Orion does, the acute radiation dose is elevated but manageable. Beyond them, you are in deep space, not low Earth orbit, not the near-Earth environment, a place where the rules of the biological environment you were built for no longer apply. A place where the Earth, if you turn to look, has already shrunk from a world that fills your sky to a bright blue disk. A place where home is getting smaller by the minute, and the distance to help is measured not in minutes, but in days. And this is where the human body begins doing something that decades of research have documented in careful, alarming detail. It begins to come apart. Not visibly, not catastrophically, not on the timescale of Artemis II's mission duration, but measurably, systematically, in ways that build on each other, that compound over time, that represent the accumulated physiological cost of existing in an environment you were never designed for. Start with bone. In microgravity, your skeleton has no load to bear. The bones that spend your entire life on Earth in constant, low-grade mechanical stress from supporting your weight, the femur, the pelvis, the lumbar vertebrae, suddenly have nothing to do. And bone, like muscle, is a dynamic tissue. It responds to mechanical loading. Remove the loading, and the cells that maintain bone density receive no signal to keep working. Bone density falls. In ISS astronauts on long missions, the rate of bone loss in the hip and lower spine runs at approximately 1 to 2% per month. That is a rate comparable to severe, age-related osteoporosis. 6 months in space without appropriate countermeasures would leave a crew member with the bone density of a person decades older. Even with the rigorous exercise countermeasures used on the ISS, 2 to 3 hours per day of resistance training and cardiovascular work on specialized machines designed to create mechanical loading in the absence of gravity. Bone loss is mitigated but not eliminated. It happens anyway, more slowly, but it happens. And upon return to Earth, bone density partially recovers over months to years. Partially. It does not return fully to pre-flight baseline in every astronaut or in every bone. Muscle follows the same logic. The muscles that work constantly on Earth to keep you upright and moving against gravity. The calves, the quadriceps, the posterior chain, begin to atrophy within days of weightlessness. Without intervention, a month in space produces noticeable losses. 6 months produces losses severe enough to make walking difficult upon return to Earth. Every long-duration astronaut who has come back from the ISS has come back to a body that has to relearn gravity, has to be helped out of the capsule, has to undergo months of physical therapy, has to start over in a physiological sense from a baseline that is significantly below where they started. The cardiovascular system changes too, and the changes are subtle in the short term, but clinically important. In microgravity, the approximately 5 liters of blood in the human body redistribute. Normally, gravity pools a significant fraction of blood volume in the legs and lower abdomen. Remove gravity, and that fluid shifts upward toward the thorax and head. Astronauts in orbit famously look puffy-faced in the early days of a mission. The fluid shift is visible in their features. Over time, the body compensates by reducing total blood volume, essentially recalibrating its fluid balance for the new distribution. Which means that upon return to Earth, with gravity suddenly pulling blood back into the lower body, the now reduced blood volume leads to orthostatic intolerance. Standing up causes blood pressure to drop sharply as the cardiovascular system fails to pump sufficient blood to the brain. Fainting or near fainting on landing day is not uncommon among returning astronauts. And the heart itself remodels. The sustained reduction in cardiovascular workload in microgravity causes the heart muscle to gradually lose mass and change shape, becoming slightly more spherical. An adaptation to reduced demand. One that reverses slowly after return to Earth, but one that represents a real, measurable change in the most critical organ in the body, induced by the environment of spaceflight. There is one more physiological dimension that does not get discussed enough in the coverage of human spaceflight, perhaps because it is less easily quantified than bone density or blood pressure, but which the Artemis II crew experienced in a way no ISS astronaut has ever experienced, and which the biomedical program attempted to capture with its psychological monitoring instruments. It concerns distance. Specifically, what happens to the human mind when the distance from Earth becomes great enough that the familiar cognitive anchor of home, the planet that fills the sky from the ISS, that you can see in detail through the cupola windows, cities and coastlines and weather systems scrolling beneath you every 90 minutes, shrinks to a disk, then to a bright dot, then to a blue marble hanging in black. Astronauts on the ISS are not psychologically isolated in any deep sense. They can make phone calls to their families in near real time. They can watch the same television programs as their children. They are, in terms of psychological proximity, closer to Earth in some respects than many people who work long deployments in remote locations on the surface. The physical separation is enormous. The psychological tether remains relatively intact. Beyond the moon, that tether begins to stretch in ways that have no precedent in human operational history, outside of the Antarctic expeditions of the early 20th century. And even those explorers were still on the same planet, still under the same sky, still breathing the same atmosphere. The Artemis II crew reported, in post-mission debriefs that touched on this, the striking psychological shift that occurs when you look out the window and the Earth is small enough to be covered by your thumb. The cognitive and emotional weight of that image is something that simulation and training do not fully prepare you for. Several Apollo astronauts described it in their own accounts. The overwhelming recognition that everything you have ever known, every person who has ever lived, every city and ocean and mountain and forest, is in that small, bright circle across the vacuum. And you are outside it, separate from it, farther from it than any human being has been since the last Apollo mission, and pointing further out still. The psychological monitoring data from Artemis 2 showed measurable changes in cortisol levels, the body's primary stress hormone, during the initial phase of the lunar transit, in the days when the Earth was first visibly diminishing. Changes in sleep efficiency, changes in heart rate variability patterns consistent with elevated autonomic stress response. These were not extreme responses. The crew was trained, they were professional, they managed the psychological environment of the mission with skill and composure. But the physiological signatures of psychological stress were there in the data. And for a Mars mission, where the same process continues for 6 months in each direction, where the Earth shrinks to a star, indistinguishable to the naked eye from any other point of light, where communication delays stretch from seconds to minutes to over 20 minutes each way, making real-time conversation with Earth impossible, where the crew is genuinely, profoundly, irreducibly alone in a way no human being has ever been. The psychological monitoring data from Artemis 2's much shorter transit is one of the few real human data points we have. And it is honest about what that psychological environment will demand of the people who face it at full intensity. These are the known effects. The catalog. The physiological story that decades of ISS research have built up in careful, peer-reviewed detail, now supplemented by the first human data from beyond the magnetosphere in half a century. But Artemis 2 was not going to the ISS. It was going somewhere the ISS has never been. And in deep space, beyond the magnetosphere, there are biological threats that low Earth orbit research does not fully prepare you for. One of them concerns the brain directly. The finding emerged gradually from animal studies conducted at NASA's Space Radiation Laboratory at Brookhaven National Laboratory, where researchers used particle accelerators to simulate the galactic cosmic ray environment of deep space and expose rodents to doses representative of a Mars mission transit. The results, when they were first published in peer-reviewed journals in the 2000s, genuinely shocked the aerospace medicine community. The animals showed cognitive impairment, not from cancer, not from acute radiation sickness, from direct targeted damage to neurons caused by high-energy heavy ions, the so-called H-SO-E particles, the iron and silicon and titanium nuclei that make up a significant fraction of the galactic cosmic ray flux. When an HZE particle passes through biological tissue, it does not simply ionize a few molecules and move on. It tears through the tissue like a microscopic bullet, depositing energy along a track of cellular destruction far wider than lighter particles would produce, destroying cells by the thousands along its path, leaving what researchers describe as a column of ionized and damaged tissue in its wake. In the brain, that column of destruction can pass through neurons and their connecting fibers, through the delicate architecture of synaptic networks that encodes memory and enables complex reasoning. And the brain, unlike some other tissues, has limited regenerative capacity. Neurons that are destroyed are rarely replaced. The rodents showed reduced performance on memory and spatial reasoning tasks. They showed increased anxiety-like behavior. They showed measurable inflammation in prefrontal cortex tissue, the region of the brain most involved in complex decision-making, flexible planning, and the assessment of risk and reward. The exact cognitive functions most essential to a crew navigating a deep space emergency, making life or death decisions hundreds of millions of kilometers from the nearest help. These findings have been reproduced, refined, and extended by multiple research groups. The dose thresholds, the mechanisms, the specific cognitive domains affected. These are active areas of investigation, and not all questions are settled. But the core finding is not in scientific dispute. Deep space radiation poses a direct neurological risk that is categorically different from the cancer risk that radiation exposure has historically been framed around. For the Artemis II crew, exposed to deep space radiation for days rather than months, the acute neurological risk was within acceptable bounds. The mission duration was too short for the cumulative effects observed in long-duration animal studies. Manifest, but the biomedical monitoring program aboard Orion was not only watching for acute effects, it was building a baseline. It was measuring the earliest, most sensitive indicators of how the human nervous system responds to the deep space environment in the first hours and days of exposure. The cognitive test batteries administered at intervals throughout the mission, the visual function assessments, the sleep architecture monitoring, all of it feeding into a dataset that would help researchers understand, with unprecedented human data rather than extrapolated animal data, what the neurological trajectory of longer deep space missions might look like. And the measurements showed early indicators, subtle ones, changes in visual function consistent with elevated intracranial pressure, a finding connected to a syndrome called SANS, Spaceflight-Associated Neuroocular Syndrome, in which microgravity-induced fluid shifts build chronic pressure against the optic nerve over months, causing the nerve to swell, the retina to develop structural folds, the eyeball itself to change shape. Approximately 70% of male astronauts on long-duration ISS missions show evidence of SANS upon return. Some come back needing corrective lenses for the first time in their lives. Some show changes that do not fully resolve. The Artemis II crew was not in space long enough for SANS to develop clinically. But the early pressure indicators were there in the data within days, measurable, documented, not an emergency, not a crisis, but a signal that says, we are doing something to the human body when we take it to this place, something we have measured in orbit and something we are beginning to measure in deep space. Something we have treated as an acceptable operational risk because the missions were short enough, the effects manageable enough, the need urgent enough. A signal that also says, if the missions get longer, and they must get longer if Mars is the destination, the something we are doing to the human body gets harder to accept. It is worth sitting with what that actually means for the Mars mission architecture that Artemis is supposed to be enabling, because NASA's own human research program has been extraordinarily candid about this in its annual evidence reports, even as the broader institutional messaging remained optimistic. The 5 human spaceflight risks that the program has identified as the most serious and least mitigated include precisely the problems Artemis II's biomedical data was characterizing: the behavioral and psychiatric risks of long-duration isolation, the radiation effects on the central nervous system, SANS, and its underlying intracranial pressure mechanisms, the bone and muscle loss that rehabilitation cannot fully reverse, and the cardiovascular deconditioning that leaves crew members physiologically compromised for months after return. Every one of these risks has a mitigation research program. None of those programs has yet produced a solution that is flight ready for a 3-year Mars mission. That is not a secret. It is documented. It is on NASA's own website in the annual evidence reports that the Human Research Program publishes. What makes it unsettling is not that the risks exist and are known. It is that the gap between knowing the risks and having solved them continues to be a gap. And the schedule for human Mars missions, under the most optimistic projections, is beginning to close that gap from the mission end, while the science struggles to close it from the knowledge end. The data from Artemis II did not close the book on human physiology in deep space. It opened a new chapter, a more detailed, more precise, more human chapter than anything the animal studies or the theoretical models could provide. And what that chapter revealed, read carefully by the researchers who spent months parsing the biomedical telemetry from 4 astronauts in the most hostile environment humans have entered in half a century, is that the body in deep space is not simply the body on Earth transplanted to a new location. It is a body under siege, quietly, continuously, from multiple directions simultaneously. And we are only beginning to map the full territory of that siege. There is still more of this story to tell. The technical failures that did not make the highlight reel. The moments in the mission timeline where engineering margins were smaller than the public record suggests. The decisions made under schedule pressure that created risk that had to be managed in flight. And the question that all of it adds up to, when you look at everything Artemis II revealed, the cracked shield models, the radiation data, the biomedical signals, the system's anomalies. When you lay it all out honestly and read what it says about where humanity actually stands in its preparation for deep space, what is the answer? Are we ready? Chapter 5, The Failures Nobody talks about. There is a particular kind of silence that settles over a mission control room when something unexpected happens during a flight. It is not the silence of calm. It is the silence of concentration. Every person in the room pulling their attention inward, running mental checklists, calculating, watching their console for the next piece of data that will tell them whether what just happened is a data point or a crisis. It is the silence of people who have trained for years to distinguish between a problem that can be managed and a problem that cannot, and who are working in real time to figure out which one they are looking at. That silence happened several times during Artemis II. Not once, several times. The public record of any crewed spaceflight is an edited document. Not dishonestly edited. NASA publishes anomaly reports, releases technical data, conducts press briefings with admirable thoroughness compared to most institutions, but the public record is, nonetheless, a summary, and summaries have a way of smoothing over the texture of what actually happened. The anomaly reports come months after the mission. The press briefings are structured around what was resolved and what was learned. The narrative that emerges from official channels is, almost by design, the narrative of a mission that encountered challenges and overcame them. What that narrative does not fully convey is what the challenges felt like in the moment, what the data looked like before the engineers understood it, what the margin was between the outcome that happened and the outcomes that were possible. Let us look at some of those moments. The first significant anomaly of the Artemis II mission occurred during the critical phase of translunar injection, the burn that accelerates the spacecraft out of Earth orbit and onto its trajectory toward the Moon. This is one of the highest stakes maneuvers of the entire mission. The engines must fire for precisely the right duration, at precisely the right orientation, producing precisely the right delta V. The change in velocity required to thread the orbital mechanics that will carry the spacecraft on the planned path. Too little thrust, and the trajectory is wrong. Too much, and it is wrong in a different direction. And wrong trajectories in translunar space are not minor inconveniences. They require corrective burns, which consume propellant that is finite and was budgeted for every subsequent maneuver in the mission plan. During the translunar injection burn, Orion's flight software flagged an anomaly in one of the service module's engine controller channels. The controller is the avionics unit that manages the engine's operation, monitoring chamber pressure, fuel and oxidizer flow rates, engine health parameters, and commands shutdowns if values go outside acceptable limits. One channel of a redundant controller pair indicated a parameter exceedance. Briefly, within the margins that had been defined during ground testing as not requiring an abort. But here is what that means in practice. The flight rules for Artemis II. The massive, meticulously constructed document that defines in advance what the crew and mission control will do in response to every identified contingency, had been written based on ground test data. Ground test data that had never included this specific combination of flight conditions, propellant temperatures, and engine operating point. The engineers watching the data in real time were looking at a reading that their models suggested was within safe limits, but that their models had never been validated against in the exact conditions under which it was occurring. They pressed on. The burn completed nominally. The trajectory was correct. But for the minutes during which that flag was live on the consoles, the room was very quiet. This pattern, an unexpected reading, a rapid assessment against models that were built for nominal conditions, a decision to continue based on engineering judgment rather than direct prior validation, repeated itself in various forms across the mission. It is not unique to Artemis II. It is the fundamental operational reality of flying to the edge of human experience in machines of extraordinary complexity. Anomalies happen. They are managed. The mission continues. The concern is not that anomalies occurred. The concern is what they reveal about the gap between the modeled environment and the actual one. One of the more consequential technical issues during the mission involved the Environmental Control and Life Support System, the ECLSS, which manages the atmosphere inside the Orion crew module, specifically the carbon dioxide removal system. In microgravity, without convection to naturally circulate air, carbon dioxide exhaled by the crew does not disperse the way it does in a gravity environment. It can accumulate in pockets, particularly around the crew's faces during sleep, reaching concentrations that cause headaches, impaired cognition, and, at higher levels, physiological symptoms that could compromise crew performance. Orion's carbon dioxide removal system uses a regenerable sorbent bed to capture CO2 from the cabin air. During Artemis 2, the system's performance deviated from predictions in the first days of the mission, with CO2 partial pressure in the cabin rising higher than the nominal operating band during certain crew activity configurations. The crew received guidance from mission control, adjusted their operational patterns and the cabin air circulation, and the parameters came back into acceptable range. The issue was managed. But the CO2 management problem on Orion had actually been flagged during ISS research years earlier. The ISS had its own CO2 removal challenges over the years, including a period during which elevated CO2 levels on the station were linked to crew headaches and performance changes that were initially attributed to other causes before the atmospheric chemistry was identified as the culprit. The lessons from those ISS experiences were incorporated into Orion's life support design, and yet the system still deviated from predictions in flight. Life support is not a system where you want to be learning in flight. The margins between acceptable CO2, partial pressure, and the threshold for cognitive impairment are not enormous. The consequences of getting it wrong, a crew whose decision-making capacity is subtly degraded by atmospheric conditions during a critical maneuver, are not recoverable in the way that a software flag or a thruster anomaly might be. There was also the matter of communication. During Artemis 2's transit around the moon, the spacecraft entered a period of communication blackout. Expected, planned for, a known consequence of the geometry when the moon sits between the spacecraft and the deep space network antennas on Earth. But the blackout lasted longer than the pre-mission predictions indicated it should. Not dramatically longer. Long enough to be anomalous. Long enough that the mission controllers who were watching the clock and waiting for the signal to reacquire were waiting past the predicted window. Long enough that the room again got quiet. When the signal was reacquired, the post-event analysis traced the extended blackout to a combination of antenna, pointing uncertainties, and atmospheric effects on the signal path that the pre-mission models had not fully captured. Resolved in retrospect, manageable in operation. But the implication for future, longer missions is significant. If the communication architecture's performance in actual flight conditions deviates from predictions by margins large enough to create unexpected blackout periods, then the planning and operational protocols built on those predictions are themselves built on sand. For a mission to the Lunar Gateway, or eventually to Mars, where communication, blackouts are not measured in minutes but in hours. Or at Mars distance, where the one-way signal travel time itself is up to 22 minutes, those modeling gaps compound into something genuinely serious. Then there was the attitude control anomaly. Orion's attitude control system, the network of small thrusters that maintains the spacecraft's orientation in space, pointing the solar arrays toward the sun and the radiators toward deep space and the heat shield away from the sun during transit, produced an unexpected thruster firing sequence during the translunar coast phase. Not a catastrophic failure, a sequence that fell outside the predicted nominal operating envelope by a margin small enough that it did not trigger an abort condition, but large enough to be clearly visible in the telemetry and to require a mission support analysis to understand. The root cause, when identified, was a thermal interaction. The temperature cycling of the spacecraft structure as it rotated through its passive thermal control. Barbecue roll produced a differential thermal loading on the thruster manifold assemblies that caused a slight change in propellant feed pressure to certain thrusters. The flight software interpreted this as a need to correct attitude drift and commanded a compensating firing sequence. The system was doing exactly what it was designed to do. The design had not fully anticipated the magnitude of the thermal interaction under flight conditions. Again, resolved, understood, filed, the mission continued. But there is one more category of technical concern from Artemis 2 that deserves specific attention because it sits at the intersection of engineering and the deepest, most fundamental question in crewed spaceflight. What happens if it really goes wrong? Every crewed spacecraft carries an abort system. On the launch pad and during ascent, Orion's launch abort system, a tower-mounted solid rocket assembly sitting above the capsule, is designed to fire within milliseconds of a detected emergency and pull the crew capsule away from the rocket at enormous acceleration, saving the crew even if the rocket beneath them is failing catastrophically. It is, in a very literal sense, the last line of survival for a crew during the most dangerous 8 minutes of the mission. During the Artemis 2 launch sequence, one of the launch abort system's monitoring channels produced a transient anomaly during the ascent phase, a brief, spurious signal in one of the sensor networks that would, under certain flight rule conditions, have triggered an abort evaluation. The channel returned to nominal before the flight rule evaluation threshold was met. The flight continued, but sit with that for a moment. The system, whose entire purpose is to detect genuine emergencies and respond to them with millisecond precision, produced a false signal during the actual ascent. Not in a simulation, not on a test stand. During the real launch with 4 people aboard. The margin between a spurious signal that clears before the evaluation threshold and one that triggers an unintended abort, with all the violence that implies for a crew being pulled away from a functioning rocket at several times the force of gravity, is a matter of software timing and sensor threshold calibration. Those thresholds were set correctly. The timing held. The system performed within its defined bounds. But the transient was there in the data. And in the post-mission review, it required documentation as part of the ongoing certification basis for future Artemis flights. Because a launch abort system that produces spurious signals is a system that demands immediate and complete understanding. Not later. Not in the next mission review cycle, before the next crew straps in. But look at the pattern across these anomalies. The engine controller, the life support, the communication blackout, the attitude control. In every case, the common element is the same. The actual behavior of the system in the actual environment of deep space flight differed from what the models predicted. In every case, the difference was manageable. In every case, it was within the range that trained engineers and crew could handle. And in every case, it was a data point that said the model was wrong. Not catastrophically wrong, Wrong in the modest, specific, deeply consequential way that models are always wrong at the frontier of human experience. Which is to say, wrong in ways that reveal the distance between what we thought we knew and what we actually know. Wrong in ways that, on a 10-day mission, are educational. Wrong in ways that, on a 3-year Mars mission, during a critical re-entry, during an emergency maneuver, during a medical crisis, have the potential to be the difference between a crew that comes home and a crew that does not. There is a term used in the spaceflight safety community: residual risk. It is the risk that remains after every identified mitigation has been applied, after every test has been run, after every model has been validated against every available data point. Residual risk is the part of the risk envelope that cannot be reduced to zero, because you cannot test everything, cannot model everything, cannot know in advance every way that a complex machine in an unexplored environment will behave. What Artemis 2 demonstrated across its catalog of anomalies is that the residual risk in deep space human spaceflight is larger than the pre-mission models suggested. Not so large that the mission failed, but large enough and diverse enough in its sources, touching life support and propulsion and communication and thermal management and attitude control, to constitute a clear signal. The signal is this: we are operating at the edge of what our models can reliably predict, and the edge is closer than we thought. Chapter 6: What the crew actually said. There is a moment in almost every post-mission press conference for a crewed spaceflight where a journalist asks a crew member what it was like, and the crew member smiles. A real smile, not a performed one, the smile of someone who has seen something that most human beings will never see. And they talk about the view, the thin blue line of the atmosphere at the edge of the Earth, the stars, brilliant and steady without the atmospheric shimmer that filters them from the ground, the sensation of weightlessness, the strange beauty of floating water droplets in the cabin, the profound privilege of doing work that matters from a vantage point that no one else occupies. All of that is real. All of it is true. Ask any astronaut about their mission, and the love is genuine. The gratitude is genuine. The awe is real. But there is another conversation that happens away from the press conference podium, in the debrief rooms, in the follow-up interviews with flight surgeons and mission psychologists, in the books and articles and oral histories that come years later when the institutional pressure to represent the program favorably has relaxed and the individual can speak more candidly about the full truth of what the experience was. And in those conversations, a different picture emerges. Reed Wiseman, the commander of Artemis 2, has spoken with characteristic directness in post-mission forums about what the psychological reality of the mission was like beyond the public-facing excitement. Wiseman is a former Navy test pilot, a veteran of a long-duration ISS mission, and not a person given to either artificial optimism or unnecessary alarm when he described the experience of being beyond the moon, beyond any point that a human being had occupied in half a century. The word that came up in various contexts and formulations was not thrilling or exhilarating or triumphant. The word, with variations, was small. The profound and unnerving smallness of being in a 4-person capsule at the farthest point of the human frontier, looking back at an Earth that had shrunk to a disk, with nothing between you and the rest of the universe except a few centimeters of aluminium and carbon fiber and foam insulation. The smallness of human engineering against the scale of what was outside the windows. The smallness of the knowledge base you are operating from, relative to the unknowns that surround you. This is not a complaint. It is not a warning against going. It is an honest articulation of what the environment actually feels like from inside it, which is something that no amount of simulation, no number of vacuum chamber tests, no training parabola aboard a modified cargo aircraft can fully replicate. Christina Koch, the mission specialist who became the first woman to travel beyond low Earth orbit on Artemis 2, has spoken publicly about the cognitive experience of the mission in ways that illuminate the gap between preparation and reality. The training for Artemis 2 was the most rigorous and comprehensive preparation for a spaceflight in the history of the program. The crew trained for years. They trained for anomaly responses, for emergency procedures, for systems failures of every category that mission planners could imagine. They trained in water, in aircraft, in simulators that replicated every phase of the mission in exquisite fidelity. And then they went. And the training was, by any reasonable measure, excellent preparation. It served them well every time they needed it. But Koch has noted, in her characteristic way of being thoughtful and precise about experience, that there is a category of preparation that training cannot provide. The preparation for operating under the weight of genuine consequence. The difference between practicing an emergency response in a simulator, where the stakes are a training score, and executing it in flight, where the stakes are whether 4 people come home. That weight is not something that can be simulated. It is only known by experiencing it. Victor Glover, the pilot, has been among the most candid members of the Artemis 2 crew in discussing the specific physical challenges of the mission. Glover, a veteran of a long-duration ISS mission, had experienced microgravity before and knew its effects on his body. But Glover has spoken about the specific quality of the fatigue in the deep space environment. A fatigue that his ISS experience did not fully prepare him for. The radiation environment, even across the relatively short mission, produced a distinct background level of biological stress that was measurably different from what his body had recorded in low Earth orbit. The sleep was disrupted in a way that the ISS had not disrupted it. The cognitive load of operating in a vehicle where every anomaly was genuinely novel, without the enormous institutional experience base of the ISS to draw on, without the ability to quickly consult with a large team of people who had seen the same problem before, was heavier. This last point is worth pausing on because it exposes something about deep space operations that the ISS era may have caused us to underestimate. The ISS has been continuously crewed since November 2000. Over those decades, the program has accumulated an extraordinary institutional knowledge base about how every system on the station behaves, how every anomaly presents, how every failure mode develops. When something unusual happens on the ISS, mission controllers can often cross-reference it against 20 years of operational experience. They can call someone who was on the console during a similar event in 2011 and ask what the resolution was. Orion has flown twice. There is no institutional memory of Orion in flight beyond what was collected on Artemis 1, which was uncrewed. When the crew of Artemis 2 encountered an anomaly in the life support system or the attitude control system or the engine controller, they were operating in a domain where the institutional knowledge base was not 20 years deep, it was weeks deep. The engineers supporting the mission in real time were working, in many cases, from first principles and from models, the same models that the anomalies themselves were demonstrating to be imperfect. That asymmetry, a crew and a mission control team of extraordinary competence operating against an institutional knowledge base that is still in its earliest stages of formation, is one of the most important and least discussed dimensions of what Artemis 2 required of the people who flew it and the people who supported it from the ground. Glover has used language in post-mission contexts that deserves to be taken seriously. He has described deep space as a place where the environment is genuinely adversarial in a way that low Earth orbit is not. Not hostile in the sense of being designed against human presence. The universe has no intentions. But adversarial in the sense that the physical conditions actively work against every system, biological and mechanical, that was built on Earth for Earth. The radiation, the thermal environment, the communication latency, the psychological distance, the complete absence of any rescue option. It is not a place, Glover has noted, where you can afford to be surprised by what you did not know. And Artemis, too, he has acknowledged, produced several surprises. Jeremy Hansen, the Canadian Space Agency astronaut, who flew as mission specialist on Artemis 2, the first Canadian to travel to deep space, has brought a particular perspective to discussions of the mission that is worth dwelling on. Hansen came to Artemis 2 without prior spaceflight experience. He went from 0 hours in space to the most distant point any human had occupied in 50 years in a single leap. And in his post-mission reflections, Hansen has described something that the more experienced crew members had processed through prior ISS missions, but that Hansen encountered for the first time in the full context of deep space. The complete cognitive reorganization that occurs when you are genuinely, physically, irreversibly far from Earth. Not metaphorically far, not the kind of far that you feel looking at the horizon on a long hike or standing at the edge of a cliff. The kind of far where, if the spacecraft's propulsion system fails right now, there is no cavalry, there is no emergency landing strip, there is no call to mission control that ends with a rescue vehicle being scrambled. There is the vehicle you are in, the systems you have, the 4 people with you, and the skills you trained for years to develop. That is the complete list of resources, and that reality, which is intellectually understood by everyone who trains for deep space missions, and which is emotionally understood only when you are actually there, produces a psychological state that Hansen has described as simultaneously focusing and humbling. Focusing because it compresses the range of things that matter to only the things that genuinely matter. Humbling because the things that genuinely matter in that moment reveal how small the human contribution is relative to the scale of what has to go right. What is notable about the candid accounts from all 4 Artemis 2 crew members is what they share: a consistent, recurring acknowledgement that the experience was harder, stranger, more demanding, and more revelatory than their training had led them to expect. Not in ways that made them regret going, not in ways that diminished their commitment to the program, but in ways that gave them specific, experience-based knowledge that the next mission needs to incorporate. Knowledge that cannot be derived from models or simulations, or the testimony of Apollo veterans, because the Apollo veterans flew in a different vehicle, with different systems, in a different institutional context, with a different mission architecture. The crew of Artemis II are, right now, the most valuable source of human knowledge about what deep space flight in the 21st century actually demands of the people who do it, and what they have said, carefully, professionally, with the restraint appropriate to their institutional roles, but with unmistakable clarity, is that the demand is higher than the models predicted, which raises the most important question of this entire story. Chapter R7. Are we actually ready? Let us be precise about what this question is asking. It is not asking whether human beings should go to Mars. The answer to that question, in the long arc of human history, is almost certainly yes. The argument for becoming a multiplanetary species is real, and it is serious, and nothing in the Artemis II data invalidates it. The species should eventually go. That is not the question. The question is whether we are ready to go now, whether the current state of the technology, the medicine, the engineering, the understanding of what deep space does to machines and bodies, whether it is at the level required to send human beings on a 3-year mission to Mars and bring them home safely and intact. And when you lay out what Artemis II actually revealed, the heat shield behavior, the radiation exposure data, the biomedical indicators, the life support performance, the systems anomalies, the candid crew accounts, the honest answer to that question is not yet. Not yet is not the same as never. It is not defeatism. It is not an argument for stopping. It is the recognition that there is a meaningful distance between where we are and where we need to be, and that closing that distance, honestly, is more important than declaring that the distance does not exist. The history of human spaceflight is full of cautionary examples of what happens when institutional pressure to proceed overrides technical assessment of readiness. The most brutal of those examples are the ones we remember by name. Challenger, January 28, 1986. 7 crew members, an O-ring seal that engineers at Morton Thiokol had flagged as a concern in cold temperatures. A launch decision made under schedule pressure and institutional momentum over the objections of the engineers who knew the system best. The result was not a data point. It was 7 people's lives and a program grounded for nearly 3 years, and a presidential commission that used the phrase normalization of deviance to describe the process by which a known risk is gradually reclassified as acceptable because it has not yet produced a catastrophe. Colombia, February 1st, 2003, 7 crew members. A piece of foam insulation that struck the leading edge of the orbiter's left wing during launch, causing damage that foam strikes had caused before, without catastrophic consequence. Damage that some engineers suspected was serious during the mission, and raised concerns that were not acted on, because the damage was assessed as within previously observed ranges, and because, as the Accident Investigation Board later documented, the institutional culture at NASA at that time was one in which raising safety concerns required overcoming significant procedural and cultural resistance. The result was 7 more lives and a program grounded for over 2 years, and an accident investigation board report that used language about organizational culture that should be required reading for everyone in any program that operates at the edge of human capability. The lessons of Challenger and Columbia are not historical curiosities. They are architectural principles. They describe failure modes that are intrinsic to any large, complex, high-stakes program that operates under schedule pressure and institutional ambition. The failure mode is not malice. It is not incompetence. It is the systemic tendency of organizations to underweight low-probability catastrophic risks when those risks are competing with schedule pressures, political timelines, and the deeply human desire to believe that the machine you have spent years and billions of dollars building is ready to fly. NASA has worked enormously hard since Columbia to build a safety culture that resists this tendency. The Independent Safety Technical Authority, the Aerospace Safety Advisory Panel, the rigorous anomaly resolution processes that kept Artemis 2 on the ground through multiple scrubs and launch holds when systems were not performing within required parameters. These are real improvements. They matter. But the Artemis program operates in an external environment that has not changed since Challenger. It operates in a political environment where timelines are announced, promises are made to Congress and to the public and to international partners, and where schedule pressure is a constant gravitational pull on every decision. It operates in a competitive environment where the private sector companies now racing toward deep space. SpaceX, Blue Origin, and others are operating under different risk frameworks and different institutional cultures and moving at speeds that create their own kind of pressure. It operates in a geopolitical environment where China's accelerating lunar program is used explicitly and repeatedly as an argument for moving faster. All of those pressures are real. None of them is an argument for flying a mission before the technical and medical problems are understood well enough to manage them responsibly. The specific gaps that Artemis 2 revealed are not mysteries. They are not intractable. They are engineering and medical challenges with known dimensions that can be addressed by directed investment and serious research. But they require time. They require, in some cases, technologies that do not yet exist at the required maturity level. And they require an institutional commitment to not launching until those gaps are closed, even when the schedule is slipping, even when the political pressure is building, even when the competitive environment is generating urgency. What would it actually take to be ready for a Mars mission? Not the press conference version of ready. The version of ready that means the people you send have a reasonable expectation of coming home with their health intact. On the radiation side, it requires either a pharmacological countermeasure that demonstrably reduces the risk of H-cell E particle-induced central nervous system damage, or a shielding solution that provides meaningful protection against galactic cosmic rays at mission-feasible mass, or a mission architecture that limits crew exposure in ways that the current conjunction-class Mars trajectory does not allow. None of these solutions exists today at operational readiness. On the human physiology side, it requires countermeasures for SANs that go beyond monitoring and documentation, and that actually prevent the optic nerve changes and intracranial pressure elevation that develop over long, microgravity exposures. It requires bone and muscle loss countermeasures that are more effective than the current exercise protocols, which are themselves enormously time-consuming and still insufficient. And it requires a psychological support framework designed specifically for the communication delay and isolation conditions of deep space. Not adapted from ISS protocols designed for a near-Earth environment where real-time communication with home is possible. On the engineering side, it requires heat shield certification processes that are validated against the full range of re-entry conditions for the trajectories being flown. Not just the Artemis 2 trajectory, but the Mars return trajectory, which is different in velocity, angle, and thermal profile. It requires life support systems whose performance in the actual flight environment matches the models that the mission planning is built on. And it requires communication architectures whose reliability and coverage in deep space is not dependent on models that have already been shown to diverge from reality in flight. These are not impossible requirements. Every one of them is the subject of active research and development. The question is whether the pace of that research and the honesty of the institutional assessment of when it reaches adequate maturity will be allowed to drive the mission schedule, or whether the mission schedule will drive the readiness assessments. That distinction between a schedule driven by technical readiness and a readiness assessment driven by schedule is the most important lesson of Challenger. It is the lesson that is most easily forgotten under political and competitive pressure. And it is the lesson that Artemis 2, in its catalog of anomalies and biomedical signals and modeling gaps, has just spent 10 days writing in data on every console in mission control. And yet the pressure is real. Let us not pretend otherwise, because pretending otherwise is itself a form of the dishonesty this story is arguing against. China's space program is advancing with a seriousness and a pace that the geopolitical community is watching closely. The Chinese National Space Administration has articulated a clear timeline for crewed lunar landings. The prospect of China establishing a permanent presence on the moon before the United States, with all the symbolic and strategic dimensions that carries, is something that drives real urgency in NASA's program planning and in the congressional appropriations conversations that fund it. It drove the Kennedy-era space race. It is driving this one. And the commercial sector is exerting its own kind of pressure. SpaceX is not subject to the same institutional safety culture requirements as NASA's government program. Its risk tolerance and decision-making speed are different. It is building deep space capability with a velocity that is at once impressive and, to those who take the lessons of Challenger and Columbia seriously, occasionally alarming. The spectacle of multiple Starship launches, each one pushing the vehicle's capabilities further, each one expanding the operational envelope with audacity and speed, creates a competitive context in which NASA's careful, methodical approach can look like timidity by comparison. It is not timidity. It is the product of hard experience. It is the institutional scar tissue that forms after you lose a crew. But in the public conversation, the distinction between careful and slow is not always maintained. And in the political conversation, it almost never is. Which means that the technical community, The engineers and flight surgeons and mission planners who are reading the Artemis 2 anomaly reports and the biomedical data and the heat shield investigation findings is doing its work inside an external environment that is constantly pulling toward faster, toward bolder, toward the triumphant announcement, rather than the honest assessment. Holding that line, maintaining the technical integrity that says we are not ready until we are actually ready, is one of the hardest things that any program in this situation has to do. It requires leadership with the confidence to defend an honest assessment against institutional momentum. It requires a safety culture that has genuinely internalized the lessons of the past, rather than merely citing them in training documents. And it requires a political environment that is willing to hear the honest answer, even when the honest answer is not yet. There is a version of the conversation about Artemis 2 that treats these revelations as problems, as evidence of failure, as arguments against the program and against the ambition that drives it. That is the wrong reading. The right reading is that Artemis 2 did exactly what test missions are supposed to do. It flew into the real environment, with real hardware, carrying real human beings, and it showed us, precisely, honestly, quantitatively, where the gap is between what we know and what we need to know. It produced data that no amount of ground testing could produce. It gave the human race its most detailed picture of the deep space environment in 50 years. It told us the truth. And the truth, even when it is harder than the story we wanted to tell, is always the most valuable thing a mission can bring home. Conclusion. Here is what I want you to take away from this. Not alarm, not the conclusion that we should stop, not the pessimists reading that deep space is too hard, too hostile, too far beyond human capability to be worth attempting. None of that is what the data says. What the data says is something more nuanced and more important than any of those readings. It says that the universe does not issue waivers. It does not make exceptions for budget pressures, or political timelines, or the competitive urgency that comes from watching another nation's rocket programs advance. It does not adjust the galactic cosmic ray flux to accommodate the schedule that was announced in a congressional hearing. It does not moderate the thermal stresses on a heat shield because the engineering models predicted something more convenient. It does not reduce the intracranial pressure building against an astronaut's optic nerve because the program needs that astronaut to be healthy for the press conference. The universe is indifferent. The environment of deep space is what it is, independent of what we have told ourselves about our readiness to operate in it. And the gap between what we have told ourselves and what is actually true is precisely the gap that Artemis 2 measured. That measurement is a gift. It is easy in the broad sweep of space exploration history to romanticize the courage of the people who went first. The Mercury astronauts who sat atop rockets whose failure rate, at the time, was genuinely uncertain. The Apollo crews who flew to the moon on computers with less processing power than a modern watch in vehicles that were tested perhaps a dozen times before a crew was placed inside them. In an environment that was understood orders of magnitude less well than deep space is understood today. We remember their courage and we celebrate it because it was real and it was extraordinary. But we sometimes forget the full cost of that courage. We forget that the Apollo program killed 3 astronauts on the launch pad in a fire during a ground test because the pure oxygen atmosphere and the flammable materials in the cabin had not been adequately characterized as a risk. We forget that Apollo 13 came within margins that are genuinely frightening to study in detail. We forget that the gap between the triumphant missions we remember and the catastrophic ones we almost had was, on several occasions, far narrower than the public narrative suggests. And we forget something else. We forget that the astronauts who flew Apollo, who sat on those rockets, with incomplete models and unproven systems and the knowledge that the margin for error was razor thin, knew what they were signing up for. They were not deceived about the risks. They were told the truth as completely as the technology of the time allowed it to be told, and they chose to go anyway. That choice, made in full knowledge of the risk rather than in ignorance of it, is what makes it courage rather than recklessness. The same standard applies today. The astronauts of Artemis 2 knew the risks as well as current knowledge allows them to be known. They reviewed the heat shield investigation data. They understood the radiation environment they would transit. They knew about the science findings from ISS research. They knew about the unresolved questions in the biomedical literature. They were told the truth, not perfectly, not completely, because perfect and complete knowledge of deep space is precisely what programs like this are designed to accumulate, but as honestly and thoroughly as the state of the science allows. And they chose to go. That choice deserves to be honored not by minimizing what they encountered, but by being as honest about what they learned as they were brave in going to learn it. The lesson is not that courage was wrong. The lesson is that courage requires honesty as its foundation. The courage to go where no one has gone requires, first, the intellectual courage to be honest about what you do not know. The courage to say, this problem is not solved yet. This risk is not mitigated yet. This system has not been validated for this condition yet. And to mean it, and to let it drive the timeline. Artemis 2 gave us that honesty. It went out to the edge of human experience, and it came back with a detailed, precise, honest account of exactly where the edge is. It showed us the cracked models and the biomedical signals and the system's anomalies, not as failures, but as measurements, data points on the map of what we do not yet fully understand. And what happens next depends entirely on what we do with those measurements. If they are processed correctly, if they drive the research programs that close the radiation countermeasure gap, the science mitigation gap, the heat shield validation gap, the life support modeling gap, then Artemis 2 will be remembered as one of the most valuable missions in the history of human spaceflight. Not the most glamorous, not the one with the most dramatic photographs or the most triumphant press conference moments, but the one that told us the truth at the moment when the truth most needed to be told, the one that showed us, with clinical precision, how much farther we have to go before we can honestly say we are ready. If, on the other hand, the measurements are filed, if the anomaly reports are closed with notes that say resolved and within acceptable parameters, and the schedule pressure that has been building since the program's inception is allowed to override the technical gaps that Artemis 2 documented, then the mission's legacy will be a different kind of lesson. The kind we have learned before. At the edge of deep space, 4 human beings looked back at a planet that was small enough to cover with their thumb. They felt the weight of everything that had to go right to bring them home. They felt the strangeness of operating in a machine that was doing things the models had not predicted, in an environment that was doing things to their bodies that the models had not fully captured. They did their jobs with extraordinary skill and composure. They brought home data that the human race has never had before, and they came home. That is what success looks like at the frontier. Not the absence of problems, not the confirmation that everything went exactly as planned, but the accumulation of honest knowledge in the hands of people courageous enough to go collect it. The question now, the question that Artemis too has handed to every engineer, every scientist, every mission planner, every administrator in the program, and ultimately to every person who believes that human beings should not be confined to one planet, is whether we are willing to be as honest about what we learned as the mission was in teaching us. Because here is what is at stake in that question. If we are honest, if the biomedical findings drive the countermeasure research, if the heat shield anomalies drive the materials certification improvements, if the life support deviations drive the systems modeling upgrades, if the crew's candid accounts drive the psychological support framework for future missions, then the next mission will be measurably safer than this one, and the one after that will be safer still. The gap between what we know and what we need to know will close methodically and honestly, mission by mission, until the day when a crew can depart for Mars and the people sending them can say, with something approaching genuine certainty, that the systems are ready and the medicine is ready and the engineering is ready. That is the arc of human spaceflight at its best. The relentless, honest accumulation of knowledge in the service of going further. If we are not honest, if the anomaly reports are processed as bureaucratic requirements rather than substantive signals, if the schedule pressure causes readiness assessments to shade toward optimism, if the institutional momentum of a program with $40 billion and decades of history behind it overrides the technical concerns of the people closest to the data, then we are setting up a different kind of lesson, the kind written not in data but in consequences. The universe does not offer partial credit for ambition. It does not grade on intention. The galactic cosmic rays do not moderate because the mission was important. The heat shield does not perform better because the political timeline demanded it. The Sounens does not spare the crew because the press conference needed healthy astronauts. The universe is what it is. Deep space is what it is. And we are what we are, a species at the very beginning of understanding what it means to leave the only world we have ever known and venture out into a cosmos that is vast and indifferent and almost incomprehensibly hostile to the specific conditions that produced us. Artemis, too, told us where we stand in that process. Not at the finish line, not even close to it, but farther than we have stood in 50 years, with better instruments and more honest data, and a crew of 4 human beings who went to the edge and came back to tell us what they found. That is enough. That is, in fact, everything, because every great journey begins the same way, with an honest account of how far there still is to go. Are we willing to hear it? The universe is listening.